Thank you, everyone. It is my pleasure today to talk to you about the deep ocean and the challenges that it faces. I'd like to talk about the intersection of deep sea discovery and biodiversity with climate change, with the rising pressure of resource extraction, and how this comes together to create a science policy interface where we as scientists become very, very important. I'd like to start beginning. Over 1,000 years ago, sailors on the ocean had a perception of the deep ocean as a place of mystery and terror, with monsters such as the Norse Kraken depicted here as being what lives in the deep ocean. About the 1850s, an era of discovery began with vessels circumnavigating the ocean and sampling the deep sea, and these revealed an environment that scientists believed to be cold, dark, salty, have high pressure. Scientists thought this was a muddy, homogeneous, and very stable and quiet environment that was food limited, essentially a massive desert that looks like the image you see here. However, in the last 60 years, there have been many new exploration tools developed that have revealed a wealth of environmental heterogeneity. We have multi-beam sonar used to map the ocean floor at high resolution. We have acoustic tools that have revealed to us gas bubble flares, such as those that come from methane seeps, or the daily diurnal migrations of plankton moving up and down in the water column. We have human-operated vehicles or submarines. We have remotely operated vehicles. We have towed camera sleds and autonomous underwater vehicles, all of which have revealed imagery of the seafloor and given us access to samples from the seafloor. And then we have new kinds of platforms with chemical sensors, such as the wire flyer. Multi-beam sonar has been so important in revealing this heterogeneity, and the Palmahim disturbance off Israel is one very good example. What these explorations have revealed, in fact, in recent years is that the deep sea is not a single ecosystem. Instead, it is a whole series of different ecosystems. Just as we have mountains and deserts and valleys and plains on land, we have many systems in the deep sea. We have vast areas of low oxygen called oxygen minimum zones. We have large plains covered with polymetallic nodules, a bit called abyssal plains. We have tens of thousands of seamounts, underwater volcanoes dotting the deep ocean floor. We have thousands of canyons and fjords cutting our continental margins. We've discovered chemosynthetic environments that rely on sunlight. that rely on chemical energy rather than photosynthesis and sunlight, such as methane seeps, hydrothermal vents, brine pools. We have discovered that the animals on the seafloor, like cold water corals and sponges, can form massive reefs that extend for many kilometers and in themselves form habitat. And we have perhaps the least studied of the deep sea environments, the deep pelagic, with tremendous amount of biodiversity. In fact, each of these habitats supports its own species with specialized features that yields very high biodiversity in the deep sea. Many of these environments have extreme conditions, and the animals that have evolved to live there have what I call superpowers. They are adapted to extreme temperature. The worms at hydrothermal vents can live at the hottest temperatures known for animal life. They're adapted to very high hydrogen sulfide at methane seeps, which is normally toxic, but the animals here, like the worms, can and live at these high levels. They are adapted to extreme pressure, such as found in our deep sea trenches. This amphipod can live at 800 times the pressure that you and I are tolerating. We have animals that can live at almost no oxygen. These include fish and some of the worms that you see depicted here. And we have animals that can calcify, form their shells and skeletons at excessively low pH, such as occurs at some hydrothermal vents. There are other kinds of superpowers. We have animals that can digest wood due to cellulose digesting symbiotic bacteria that live in them. These would be xylophaga. We have animals that, like the osedax, the whale worms, that can digest lignin, again, with the aid of symbiotic bacteria. My favorite superpowers are the powers of extreme longevity. We have fish in the deep sea that typically live for 100 or even 200 years. The oldest living fish is the Greenland shark, can live up to 400 years. We have deep sea tube worms at methane seeps that can live at least 300 years. But in fact, all of these are quite young compared to some of the deep sea corals. We have Leopathes and Gerardia, which can live for thousands of years. And in fact, the Leopathes is one of the genera found in the Palmahim disturbance. And the oldest known taxa are some of the deep sea sponges, which can live for up to 17 or 18,000 years. So while we have been discovering all this biodiversity, the ocean has been changing as a result of carbon dioxide emissions warming the atmosphere. And we know the ocean is the greatest climate mitigator. It's taken up 93% of the excess heat in the atmosphere. This has caused changes in both solubility and stratification, which have led to loss of oxygen. We call this ocean deoxygenation. And it's led to reduced nutrients upwelling to the surface and general productivity decline. The ocean has also taken up almost 30% of the excess carbon dioxide, and this is led to what we call ocean acidification. And while all these changes occur at the sea surface, both heat and carbon dioxide are being transferred into the deep ocean by thermohaline circulation and convection, and this has led to a warmer, more acidic, and less oxygenated deep ocean. Some of the effects of these changes include the redistribution of species and the release of methane by warming. We also know that tuna are migrating into different regions of the ocean as a result of warmer water. Loss of oxygen has caused biodiversity loss and the alteration of food webs. It's also compressed the habitats of many billfish and large, rapidly swimming organisms in the open ocean. We know that acidification is leading to the dissolution of deep water coral reefs, especially the non-living parts of these reefs. We've come to understand that the marine life, including in the deep ocean, plays critical roles for the carbon cycle. The biological pump, which starts with uptake of carbon dioxide at the surface by phytoplankton and leads to sinking of organic matter, leads to sequestration of carbon on the seafloor. But it's important to remember that the different marine mammals and fish stocks, with their vertical migrations and horizontal migrations, play a major role in removing, transporting, transforming, and burying carbon in the sediments. Deep sea species also account for a lot of nutrient regeneration that ultimately makes its way back to the surface and fuels productivity and all of our fisheries. We've come to recognize that all the heterogeneity that I've been speaking about on the deep sea floor, in addition to providing biodiversity, provides many carbon services. Some of these habitats, like the margin habitats, canyons, fjords, and oxygen minima, have very high rates of carbon preservation and sequestration. Others are very vast and account for a lot of carbon. Some sequester carbon in large amounts of biomass on seamounts and cold water coral and sponge reefs. Some support productivity, such as and nursery habitats. And again, here's an example from off of Israel. We recognize that methane seeps provide a critical filter for methane, which is a very potent greenhouse gas, and both the animals and microbes there keep it from making its way into the atmosphere. And we recognize that hydrothermal vents play a very key role in ocean fertilization, again, supporting primary productivity. So as we've come to understand that the deep sea is heterogeneous, biodiverse, but suffering from the effects of climate change, we also have a growing human imprint on the deep ocean. Our population has been growing very rapidly and now exceeds 8 billion people, and this has led to demand for more food, more energy, more raw materials, and especially for metals and rare earth elements to fuel electronics and our green technology revolution. We also are looking to the ocean for more medicines. And as we exploit or run out of these resources on land, we look to the ocean, and as they're depleted in shallow water, we move into deep water. It turns out that all of this habitat heterogeneity that I've been describing also is led to generation of resources. For example, oxygen minimum zones have bacteria that sequester phosphorus and yield phosphorites, which are now of interest for mining for fertilizers. The abyssal plains have polymetallic nodules, the seamounts have cobalt crusts, and the hydrothermal vents have massive sulfides, all that have cobalt, nickel, copper, and other rare metals of interest for green technologies, electric car batteries, for example. We know our canyons sequester oil and gas. We have aggregations of fish on seamounts and at methane seeps, and in some cases at cold water coral reefs and sponges, especially for juvenile fishes, but these have fueled massive fisheries. We're looking at new mesopelagic fisheries, and we're looking again at deep sea organisms, especially sponges, as for their ability to produce new drugs and pharmaceuticals. So there's a lot of resource extraction interest, and it used to be the deep sea was a pristine environment, pretty much immune from human effects because we could not get there. We now have a whole series of technologies that have enabled us to access resources anywhere in the deep ocean. We have satellite-guided GPS and sophisticated mapping tools. We have cables and fishing gear and oil and gas infrastructure that can reach any depths. And we're now developing new tools for mining minerals on the deep seabed. We've begun to fish continuously deeper, and it's now routine to fish below 1,000 meters. This has led to overfishing of long-lived fish species. It's led to ghost fishing by lost fishing gear, which continue to harvest fish without ever being collected. It's led to the endangerment of species which are not targeted but are collected as bycatch. And it's led to damage of the three-dimensional structures created by coral sponges and other organisms on the deep sea, essentially harming biodiversity. We are drilling for oil and gas continuously deeper. It's now routine to drill at 3,000 meters or more. And this has raised many environmental concerns from discharges of cuttings and fluids, but also from spills and blowouts. One of the most famous of these is the Deepwater Horizon here in the Gulf of Mexico. But we also have come to understand that extracting fossil fuels is continuing to exacerbate climate change and that this cannot be sustainable. I mentioned 3 ecosystems targeted for mining in international waters. These are polymetallic nodules on abyssal plains. There are cobalt crusts on seamounts, and there are massive sulfides at hydrothermal vents. And each of these ecosystems supports distinct types of biodiversity. There are now 31 international exploration contracts for deep seabed mining for these resources. This in international waters, the resource is regulated by the International Seabed Authority. In national waters, there are also interests in mining deep sea minerals with the motivation of getting these rare minerals for electric car batteries and electronics, wind turbines, and solar cells. We know that mining at the sea floor will create many different kinds of disturbance, light, sound, and vibration. There will be physical disruption and removal of animals. There will be smothering and clogging of feeding apparatus by suspended sediment plumes. There will be altered geochemistry and altered substrate. There will be release of contaminants, loss of structure, changes to food webs, and many more types of disturbance. Humans are also disturbing the deep sea through waste disposal, both intentional and unintentional. Examples include the DDT waste barrels shown here, which were dumped by the thousands off of Southern California about 50 years ago, with these long-lived contaminants still present. There's a lot of plastic waste. There's different kinds of unintentional debris. There's intentional mine tailings disposal from land. And increasingly, we're looking at disposing of carbon dioxide and organic matter bearing carbon into the deep ocean as a way to mitigate climate change. So we are faced now with the challenge of how to manage these different forms of human disturbance at the same time that the resilience of the deep sea is being challenged by climate change. And management, of course, involves different jurisdictions. We can look at who owns the ocean. 154 countries have coastal ocean. 48 do not, and these countries own the area you see in blue, the exclusive economic zones, and some have claimed extended continental shelves shown in red, but fully 60% of the ocean is international. These areas beyond national jurisdiction are managed by a variety of UN agencies in a highly sectoral manner. So there are different treaties and organizations managing biodiversity, fisheries, seabed mining, pollution, climate, science, and even conservation. We are faced with how to manage all of these aspects together, and I think it's important to recognize that biodiversity and climate are fundamentally intertwined. Let me go back a minute. In the deep sea through the carbon cycle. We need novel approaches to ensure that both biodiversity and climate are addressed together to enable sustainability of the deep ocean. One of the ways that we can actually do this is through protecting, creating protected areas. And there is a goal now to protect 30% of the ocean by 2030. I would argue that these marine protected areas need to be climate smart. We need to build both climate and biodiversity into management of the ocean, not just for MPAs, but for environmental management of these different types of resource extraction that I've been talking about. We need climate smart fishing, where we manage for carbon services alongside fishing and vulnerable marine ecosystems. And we need to bring to all of this management good science, including deep sea science. And the Deep Ocean Stewardship Initiative is one network of scientists which is dedicated to bringing science to deep sea policymakers. So I'd like to leave you now with the thought that we are at a critical time facing decisions about deep seabed mining, about climate interventions that will affect the deep sea, about energy extraction in the deep sea and fishing in the deep ocean. We are in a place where we need to take care of our ocean as alongside the needs of humans, because we need our ocean for a healthy planet. And as a result, we need to proceed with all of these and other new activities with caution. With that, I'd like to thank you for listening. I'm sorry I could not be there to join you in person. but I appreciate the invitation to speak with you.